Let's take a look at electrocyclic reactions in the case of 4-pi electron systems. And when we consider this, we're going to also go through a photochemical and a thermal kind of side-by-side comparison to see what's happening here. Just like before, we're going to end up with an anti-product and a syn product, but we've got to figure out which one is going to lead to which, right? Is the photochemical going to lead to the anti or the syn? And the thermal should be the opposite, right? Because the HOMO and LUMO would have opposite orbital symmetry. So let's leave that up, actually. Let's take a look at the orbitals. If we take a look at the HOMO, and we'll just duplicate this here. The HOMO is what's going to take part in the thermal one. And the HOMO for a 4-pi system should have one node. So we're looking at having one node in the middle here. For the LUMO, we're looking at 2 nodes. So we're looking at the opposite. Our green one's going. And we're going to look at these much the same way as before. So this is our HOMO on the left. And we have our lowest unoccupied orbital on the right. That's the one that's going to take part in the photochemical reaction because an electron will be promoted up there. So, if we take a look at the HOMO, in this example, again, we're going to have our methyl groups pointing opposite directions. So notice we have one up, one down. So they are pointing opposite directions from each other. And if we look at just the end orbitals, so on 1 and 4, we see we have purple up, purple down. And therefore, if these need to rotate together, we're going to have one rotating. Love doing this. So we're going to have one of them rotating. That would be counterclockwise. The other one would also be counterclockwise. And therefore, this is going to be a conrotatory process. And so if they're both going to be conrotatory, that means we're going to end up with our methyl groups still on the opposite sides. Since we're rotating the same direction, they were already opposite, we're rotating the same direction, they're going to stay opposite to each other. And again, try and visualize it. Use your hands. See, we've got them pointing up. They're both going counterclockwise. Poof. There we go. Opposite sides. And so, as a result, we will have one down, one up, and the enantiomer. Of course, because, again, I've rotated them both counterclockwise, you could rotate them both clockwise to get the green ones to overlap. The point is we have a conrotatory. That means that our stereochemistry doesn't change. So we had an anti-relationship before, one up, one down. We still have that anti-relationship. And surprise, surprise, if we take a look at the LUMO with a photochemical process, instead, let's draw our methyl groups. And of course, these methyl groups are just placeholders, right? It could be anything. If we can see here, since they are they're already in phase with each other, one would need to rotate one direction, the other would need to rotate the opposite direction. Today that we're going to have the green ones overlap. And as a result, because they are rotating the opposite direction from each other, since they were anti to begin with, they are now going to be syn to each other. And in this case, the rotation that I've done is going to end up putting them both, the ones that are pointing out are both going to go up. And as a result, we end up with our groups pointing up. and this is through a disrotatory manner here for UV. With light, we end up getting a disrotatory process, and we end up with the syn product. And so, if we wanted to fill this in, we're going to see that, on top is our thermal process, and we end up with our opposite processes there. And then again, if we were to do the reverse reaction, if we want them to be on the syn side, we would need UV light, and then thermal for the if they are syn and we want them to remain syn, because that one's the conrotatory. So if we compare the two, the 6 pi and the 4 pi systems, we're going to see that we can compare the conditions here. So we saw that 4 pi with light is disrotatory, and with thermal it was conrotatory. With thermal for 6 pi, that was disrotatory, and with light it's conrotatory. And really this can actually go to 4n pi electrons. And this would be 4n plus 2 pi electrons. So it doesn't necessarily mean 4 and 6, respectively. An 8 pi system would behave much like a 4 pi system would, and a 10 pi would be the same as a 6 pi system. So the point is, when you have a conrotatory, your stereochemistry stays the same. So if they are pointing opposite directions and you have a conrotatory process, in your product, they're still going to be pointing opposite directions. If you have a disrotatory process, you're switching the two. You're going from anti to syn or syn to anti. And as a result, you're going to end up switching the stereochemistry. So this is a handy little table here for you to kind of reference for when you're looking at what type of electrocyclic reaction is going to take place, and you don't want to necessarily have to draw out all the orbitals. And so as a result, you should be able to predict the product stereochemistry. And that's it for electrocyclic reactions. You'll of course have some homework practice on it. So let's take a look at sigmatropic rearrangements next. That's going to be our last section in this chapter of conjugated systems, and that'll be in the next video.